Okay, so thank you, the organizers, for inviting me. It's a pleasure to speak here. I'm going to tell today a real analog of the story of the WDBV equations in complex Gromov-Witten theory, which in some cases is also known as Kontsevich's recursion formulas. Let me start by introducing or reminding you of of what are Gromov-Witten invariants. So let X omega be a symplectic manifold of dimension 2n. Let J be an omega tame almost complex structure, and B be a homology class of X in the second homology group. Let H1 up to HL be oriented closed submanifolds of X, such that this equation here holds. It doesn't really matter what it means, just some equation. And we denote those square bracket H1 up to HL to be their homology classes in the rational homology group of X. Then the so-called genus 0 Gromov-Witten invariant here is defined to be the number of degree B rational J-holomorphic curves in X passing through H1 up to HL, where rational just means genus 0. I draw a little picture here. So I have this ambient space X. I'm counting J-holomorphic spheres in it. Degree B means its homology class is B, and it passes through all of those constraints H1 up to HL. This number is independent of the choice of generic almost complex structure J, or the choices of those representatives, those actual constraining manifolds in their homology classes, which means that this number, it only depends on the manifold X omega, the homology class B, and the homology classes of H1 up to HL. To see this, we can think of this number in the following way. Denote MLB to be the moduli space of degree B rational holomorphic curves with L marked points in X. So it's a set of tuples. It has the part of a map, which is a map from P1 to X. It's J-holomorphic, its homology class is B, and we have an additional L marked points on P1. So I take this set modulo reparametrization group of the domain, because I want elements in this moduli space to be curves in X instead of which point on P1 I call 0, which point on P1 I call infinity. So that's just modulo reparametrization of the domain. This space, for our purpose today, can be viewed as a smooth manifold. It's a complicated thing to say what it really is, but for our purpose today, we are going to view it as a smooth manifold. But it's not compact. So we denote by MLB bar to be its Gromov compactification, which is obtained simply by adding in reducible curves, which are curves looking like, which are images of maps looking like this guy here. The domain is wedges of P1 in the shape of a tree. It's mapped to X. We require it to be J-holomorphic on each component, require the total degree to be B, and we require, we just have L marked points distributed. It can be anywhere here. And as usual, we modulo the reparametrization of the domain. This is the so-called Gromov compactification. To see how this looks like, here's a picture. So I have those smooth, irreducible P1s in my manifold, but at some point they can converge to something that's nodal looking like this. So I'm just adding in this curve here to make a compactified modular space. this space can be viewed as a compact, smooth manifold. And I can define the evaluation map from this moduli space to XL, which is the direct product of X with self L times, defined by I map this U, the map part with the marked points, to just evaluating this map at all of its marked points. On the other hand, we have, remember, those closed submanifolds H1 up to HL in X, which will require the curve to pass through. So H1 direct product until HL is included into X to the L. Since both of this guy here and this guy here are or can be viewed as closed manifolds mapped into another closed manifold, we can talk about their intersection number for appropriate dimension. So this equation here just is a condition so that this count is finite instead of a higher dimensional family or something like that. So this intersection number precisely counts the number of curves in this moduli space that passes through H1 until HL. So that's our Gromov-Witten invariant. Since intersection is on homology level, it does not depend on the specific choices of representatives in their homology classes. That's why it's invariant. And similarly, if you have a family of J, you have a cobordism of such moduli spaces, it doesn't change this number either. Okay, so how do we compute those numbers? There's a very powerful way, which is called WDBV equations, that are proposed by Kontsevich in 1992 and the proof given by Ruan-Tian in 1993. The equation looks like follows. So each of this diagram, for example, this one stands for the number of degree B J-holomorphic curves in X looking like this. So it has two components, two copies of P1 wedged together, such that the first component passes through the constraints H1 and H2. The second component passes through the constraints H3 and H4. And this curve itself also passes through the rest of the constraints H5 up to HL. But those can be on either component. That's what this diagram stands for, it's such a number. And the equation just says that this number equals to this number here, which is the number of degree B J-holomorphic curves of such shape, such that the first component passes through H1 and H3, the second component passes through H2 and H4. So the only difference is the switching of H2 and H3. That's this equation. And once we have this equation together with a formula that's called splitting that expresses the count of those reducible curves in terms of counts of components, we get an equation between the usual Gromov-Witten invariants. And in good cases, like CPN, it gives full recursion formulas. So it just computes, say, all of the Gromov-Witten invariants of CPN from some basic inputs like degree 1 numbers. The idea of proof is as follows. Originally, they show, these are invariants parameterized by an element in the Deligne-Mumford space M04, which is independent of sigma, which can be interpreted as lifting a homology relation from M04. Let me elaborate on this. So M04 is the moduli space of the relative position of 4 marked points on P1, which is probably simplest Deligne-Mumford space. This space is isomorphic to P1 because cross ratio is a complete invariant. And we can define forgetful map from this moduli space of curves to M04 by just mapping this U Z1 up to ZL to the relative position of the first 4 marked points. Now, let's consider 2 special points in M04, sigma 0 and sigma infinity, which are defined to be the points such that the cross ratio are 0 and infinity respectively. When the cross, by the spirit of the Deligne-Mumford compactification, when the cross ratio is 0, that's when Z1 and Z2 come together, and Z3 and Z4 come together. So you have this sphere when Z1 approaches Z2, they bubble off. So sigma 0 is actually a nodal reducible curve like this. When the cross ratio is infinity, Z1 and Z3 coincide, and Z2 and Z4 coincide. So the sigma infinity is actually such a reducible curve like that. Since clearly they're both just points in M04, their homology classes are just a point class. So we have the pre-images of them under the forgetful map are also homologous. Because if you take a cobordism between these 2 points, you consider the pre-image of this cobordism, you get a cobordism between their pre-images. Therefore, these 2 pre-images are in the same homology class in the moduli space of curves in X. So just to mention, when I write a curly M, like smooth like this, I mean the moduli space of curves in X. And when I write like a sharp M, I usually denote it as the moduli, the Deligne-Mumford moduli space of marked points on P1. Just remark. So since these 2 submanifolds of MLB bar are homologous, we have these 2 intersection numbers being equal. But what are they? This intersection number is just the count of curves in this submoduli space, which passes through H1 up to HL. In other words, it's the count of curves. This word takes a minute to load. Yeah, it's a count of curves of such shape. So H1 and H2 are inserted to the first component. And on the other hand, the inverse image on the forgetful map of sigma infinity intersected with H1 up to HL is precisely the count of nodal curves of such shape. Therefore, this lifting homology relation thing gives me this equation here. Okay, any questions so far? No, good. Now I'm going to talk about the real analog of this story. So let me talk about what's the real analog of Gromov-Witten invariance first. Let X omega phi be a real symplectic manifold, which means X omega is a symplectic manifold, say of dimension 2n, and phi is an anti-symplectic involution. We call phi a real structure because it's the analog of the usual conjugation map on Cn. Examples are just for the, say Cpn together with coordinate-wise conjugation. We denote by x phi the locus of fixed point of phi. In the case of Cpn with the standard coordinate-wise conjugation, it's just Rpn in it. We denote by b, as before, second homology class in X. And let J be a real omega tame almost complex structure, where real just means that the real structure phi is anti-J holomorphic. We call a rational curve C in X to be real if it's phi invariant. And just as above, we take H1 up to HL in X minus X phi. This minus thing is just some technicality. To be oriented close to submanifold as before, and we take P1 up to Pk points in the fixed locus of phi, such that this equation is satisfied, which simply means that the numbers we're going to count is finite. We denote as before square brackets h1 up to hl, they're homology classes, but in the complement of the fixed locus of phi for some technical stuff. So now we can ask how many degree B real rational J-holomorphic curves in X passes through the constraint H1 up to HL, P1 up to Pk. In general, this number is not invariant. It depends on the choices of, say, J, those H1 up to HL in their classes, and the position of the points P1 up to Pk, because the real case, say, the number of zeros of a real polynomial is just not a fixed number. But however, it's a theorem of Welschinger in 2003 and 2005, respectively, in the case that X is a symplectic fourfold and sixfold, we do have such well-defined invariant numbers. We assume the fixed locus of the real structure is orientable if n is 3. So the theorem says that the number of degree B real rational J-holomorphic curves passing through the constraints, if counted with appropriate signs, is independent of those choices. Here's a picture of it. I have this ambient space X. I have a real structure phi on it, anti-symplectic involution, which in the picture looks like the horizontal reflection. And I have its fixed locus x phi here. I'm counting rational curves which are invariant under this reflection that passes through those constraints, H1, H2, P1, P2, and so on. Of course, it's a fixed homology class B. So those are called Welschinger's invariants. Solomon in 2006 gave a reinterpretation of them. And in our main theorem, it's the first step is to view these invariants again as degrees of relatively oriented pseudocycles. So we can ask the same question as before: how do we compute those numbers? Do we have a similar story like the WDVV in the complex case? And the answer is yes. In 2007, Jake Solomon proposed WDVV-type recursions for Welschinger's invariants in the case X is a symplectic fourfold. And this was proved by me in 2018. So just a proof of them. And further, if X is a simplex sixfold, it was a result of Alex Zinger and me that similar formulas hold if you assume X omega phi has some finite symmetry condition. Okay, those equations in good cases also give complete recursion formulas of Welschinger's invariants of a manifold. For example, we computed all of those numbers for P2, P3, P1 squared, P1 cubed, and the real blowups of P2. And also to mention that Solomon and Tukaczynski's 2019 paper gives WDVV equations for open Gromov-Witten invariants, which are more general, and it recovers the n equals to 3 case above. But not the n equals to 2 case, because in this case, we do not assume x phi to be orientable. For example, RP2 in CP2, for example, if we take CP2 with a standard conjugation, the fixed locus is RP2, which is not orientable. Let me show you how these equations look like. Below, I have a picture. So for fixed constants, we have these two equations. Let me explain. Such a diagram means the number of reducible nodal curves of such shape in X of total degree B, such that the top component, so it's a real curve where this phi looks like horizontal reflection in the curve. So this phi exchanges these two top and bottom components, and it fixes this component but exchanges this top and bottom hemispheres. So this sphere we call a real component, and these two spheres we call a conjugate pairs of components, or bubbles. So this diagram stands for the number of such curves where this component passes through the constraints H1 and H2 bar, which is just phi of H2. And this component passes through P1, and this curve itself also passes through the rest of the constraints, which can be on any component. That's what this diagram stands for. And the two WDBB equations are equations between those numbers, which looks like this. So once we have these equations together with splitting, which is a way to express a count of such reducible curves in terms of counting components, we get equations for Welschinger's invariants. So the left-hand side, such a count is going to be expressed in terms of count of this real curve, which is a Welschinger's component, times and also count of such complex curves, which is usual Gromov-Witten invariant. And for a nodal curve like this on the right-hand side, the count of it is just going to be expressed in terms of Welschinger's components, which are count of Welschinger's invariants, which is count of its components. Yeah, and that gives us the desired equations. Okay, before I go to the sketch of proof, any questions so far? No questions? Okay. Some of this. Yeah, because when I drew this picture, that's because actually in those equations, I'm not really counting all of the curves literally of such shape passing through those constraints. I have some conditions on it. In reality, I'm only counting curves that for some fixed distribution of degree and constraints between these components. And in addition, I also have to specify the position of the node with respect to this point on the first sphere. So there are some extra conditions that characterizes those curves that actually appears in these equations. I just didn't write it here for simple illustration purpose. Okay, any other questions? If not, let's go to the sketch of the proof. Let us denote by tau the usual conjugation map from P1 to itself, just coordinate as conjugation, which looks like have the sphere, you have this horizontal reflection. The fixed locus is simply RP1 inside of CP1. We denote by RMKLB to be the moduli space of degree B real rational J-holomorphic curves in X with K real marked points and L conjugate pairs of marked points. Here's a picture. I don't know if it's only me that the page loads slowly or you all see it loading slowly. Let me try to wait for it to load a bit. Doesn't seem to load. Doesn't seem to be loading. Should I maybe use my local notebook instead?
If you'd rather do that, that's fine as well.
Okay. Yeah. Okay. Okay. It's a little bit too slow to. Does it usually load after a few seconds? This one doesn't look like it's loading either. Should be something going here. Yeah, the sections here are also not loading.
Do you want to give yourself like a few minutes and stop sharing, then send some time to restart everything? I mean, just in case it helps.
Oh, okay.
I mean, I think we can wait. It's not.
Okay, thanks. Let me stop sharing first, and then. Yeah, okay, I just restarted OneNote and it works. Thank you. All right, so everyone can sit now, I hope. Okay, so we're back here. Okay, thanks. We're back here. We denote by RM KLB this modular space where I draw a picture. It's just like this. I have the ambient space X. I have this anti-symplectic involution, my real structure, where its fixed locus looks like drawing here. And I'm counting real curve. Oh, sorry, I'm not counting. An element in this modular space is a real J-homorphic curve, which has those conjugate pairs of marked points and the real marked points on it. Again, for our purpose today, it can be viewed as a smooth manifold. It's not compact, and again, we have its Gromov compactification, which is obtained by adding in real reducible curves, looking like something here. It's mapped from wedges of P1 to X, and we also have like tau tilde, a real structure on the domain, which in this picture, it exchanges these two components, and it fixes its two components, but exchanges their two hemispheres. So we call such two components a conjugate pair of components, and such two components real components, just as I was explaining in the picture. This space can be viewed as a compact, smooth manifold. And we can define, as usual, the evaluation map from it. A question, can you say more about what you mean by automorphism R of the domain? Oh yes, it's just the automorphism of the domain that commutes with this real structure. Okay, so in the example of P1, it's simply a Mobius transformation with real coefficients. Okay, we have this evaluation map, which evaluates this map at all of its marked points. And to prove the WDVV equations, as before, we want to lift homology relations from the manifold spaces of marked points on P1. So in reality, we're going to use these two spaces, Rm12 and Rm03, which are defined to be Rm12 is the moduli space of the relative position of one real and two conjugate pairs of marked points on P1. Is here. And Rm03 is the moduli space of the relative position of three conjugate pairs of marked points on P1. So we're going to use, and we have the forgettable map from this moduli space of curves in X to this manifold spaces Rm12 or Rm03, simply mapping this tuple into the relative position of its first few marked points. So what's the difference between the complex case? Why can't we just lift a homology relation from here? The main issue is that all of these spaces, this guy here, this guy here, and this guy here, they may not be orientable. Okay. Because we're in the real case, things are just, in the complex case, you always have complex orientation, but that's not what happens in the real case. In fact, Rm12 is just Rp2. And this fixed locus a Lagrangian, we don't require it to be orientable in the symplectic fourfold case of the theorem. So if you don't have orientable manifolds, it no longer makes sense to lift homology relations. So what we do is that we are going to lift homology, but the idea is we're going to lift homology relations from the manifold spaces together with some bounding manifolds to incorporate the wall crossing effects coming from walls that obstruct relative orientability. Okay, before I explain this idea, let me make two remarks on, let me explain first what this moduli space RMKLB bar looks like. It has the structure of a stratified space, namely, so we have curves of such shape which form codimension 1 strata in it. Curves of such shape, I mean curves that it's a reducible curve which has two components, both are real, with one node in between. So this is different from the complex case, because in the complex case, everything is of at least complex codimension 1, real codimension 2, so we don't have any walls. But in the real case, we do have such walls. And RMKLB looks like it's stratified. Some top dimensional cells consists of irreducible curves, which are just RMKLB before the compactification. It has some codimension 1 walls in it, which consists of such curves. Oh, by the way, we assume no spirit bubbling. It's actually ruled out by some necessary assumption. So we only have disk bubbling like this. Just a remark. It also has some codimension 2 or higher codimensional strata, which consists of curves with 2 or more nodes. Something like this. But for us, what's relevant are codimension 1 stuff, because when we do intersection theory, only codimension 1 things matter. It was implied in Jake Solomon 2006, his thesis, that evaluation map, although, oops, okay, I'll just keep going. Although both of the domain and target of the evaluation map may not be orientable, but when you restrict the evaluation map at the top dimensional cells of the space, so RMKLB before compactification, those irreducible curve parts, then this map is relatively orientable. By relatively orientable, I mean the pullback of the first Steve Whitney class of the target equals to the first differential unified class of the domain. Or how you really should think about it is that if you have such a map between two manifolds, X is mapped to f of X, you identify the orientation between the tangent space of X of M with the tangent space of f of X of N, and this identification of orientation needs to be continuous. There's natural definition, relatively orientable. And his thesis also shows that this relative orientation extends through some codimension 1 strata. Okay, remember, yeah, those two component guys here, but not the others. So for those strata where this relative orientation does not extend through, we call them bad strata. And those are the walls that obstruct relative orientability, which are important for us. All right, okay. What do we lift from those dilemma-manifold spaces? We take gamma submanifolds of Rm1, 2, or Rm0, 3 respectively to consist of curves of such shape. Has 3 components, a conjugate pair and 1 real, such that the first, this top component carries Z1 plus and also Z2 plus or Z3 plus minus. It was shown in Welschinger 2013 paper that this gamma here is a now homologous codimension 2 submanifold in Rm03. In the case of Rm12, it's just trivial. It's 2 points, 1 plus, 1 minus. But in Rm03, you have to show, you actually have to see that it's a now homologous submanifold. Therefore, we can take a submanifold that bounds it. Let's call it Y. So this gamma is going to be the homology relation we're going to lift because it's not homologous. And this Y is the bounding submanifold that bounds it, which we're going to use to incorporate the wall crossing effect. So we consider this intersection. I have this moduli space of curve in X maps to by the direct product of evaluation map and forgetful map to this target x5 to the k times x to L, the target of real evaluations and the target of evaluations as conjugate points. This is the manifold space, the target of the forgetful map. On the other hand, I have this inclusion map from those constraints times the direct product with this submanifold Y included in here. So for notational convenience, let me just call this direct product constraint C. We consider the intersection numbers. We assume those B, K, L are such that the following intersection numbers are finite. So we consider the intersection numbers Rm, K, L, B intersect with C times gamma, the boundary of Y, and the intersection number between the bad strata in it with C times Y. These two intersection numbers are equal. So notice that the left-hand side, if there's no orientability issue, if everything is orientable, then the left-hand side is 0 because gamma is not homologous. However, this is not the case, so the left-hand side equals to the right-hand side, which are wall crossing correction terms from the obstructions to relative orientability here. And it's expressed in terms using this submanifold Y in the manifold space. The reason why we have this equation is fairly simple. let's cut this guy open along those bad strata. Because evaluation map is not relatively orientable, we cut it open along those obstructions to relative orientability. So by cut open, I mean literally you just, like you have if you have a surface, you have a scissor, you can cut it open along a curve. If you have a higher dimensional manifold, if you have some codimensional walls, you can also just cut it open along those walls, and you get two copies of the walls as boundaries of the manifold you get. So you get Rm hat, a manifold with boundary. And now that we have this Rm hat, now if we take the intersection from Rm hat, then this part, and also this part, this part are going to be both relatively orientable. And then the boundary of this intersection, which is one-dimensional, is going to be the intersection between this manifold with the boundary of this one, plus minus the boundary of this one, intersect with this manifold. It's just elementary thing. If you have two manifolds with boundaries intersecting on something of one-dimensional, then that gives you line segments connecting something like this with something like this, which are both just finite sets of points. Therefore, this number is 0. And this intersection Rm hat with the boundary of C cross Y, boundary of C cross Y is just C times the boundary of Y, which is C times gamma, that is here, the left-hand side. And the boundary of Rm hat, on the other hand, since it's obtained by tearing Rm Kelvin bar apart along those bad strata, it's just twice of those bad strata. That gives the right-hand side here. Okay, from this equation star, we get our desired pictures here. So look, this term here, Rm hat times Rm hat intersected with C cross Y are precisely the counts of curves of shape gamma, which, as I mentioned, are curves. So it's the left-hand side of these two equations. There are curves of such shape. It has three components looking like this, where the first one carries the first and second marked point, and yeah, that's precisely how this gamma was chosen. On the other hand, since bad strata, as we remember, so those codimension 1 things are curves with two real components looking like this. So the right-hand side of these two equations are precisely coming from here. We are counting curves of such shape. Okay, so this equation we get here gives us this two picture that I showed before, where the first one is from Rm12 bar and the second one is from Rm03 bar. Now that we have these two equations, we have to split each of these counts of reducible curves into counts of its irreducible components. In the symplectic fourfold case, the left-hand side is just curves or real two-dimensional things in a symplectic fourfold. So they intersect finitely. To load. Let me see if I can. Okay, loading seems to be really slow. Maybe let me just stop screen sharing again first and restart OneNote. Okay. Okay, now should be fine. So splitting the left, if we are in a symplectic fourfold, then the count of such a nodal curve is just the count of its top component, which I mean that the count of if this nodal curve is of the top one is of degree b prime, the middle one is of degree b naught, and this one is of course of degree negative 5 star b prime because they are conjugate. Then each of this component has to be, if this nodal curve appears in this count, then each of those components has to be rigid, which means the count needs to be phi, which means the count of such degree b complex curves passing through those constraints carried by this component must be finite. So the number of such a nodal curve is just the number of such complex curves times the number of such real curves times the intersection number between them, which encodes the choice of the node. This is a completely trivial thing. And the right-hand side is a little bit complicated. So the right-hand side of this star equation is twice of bad strata intersected with the constraint times this submanifold in Rm, say 1, 2, 0, 3, right? It's a codimension 1 thing in here. And we can show that if we, with a dimension count together with a good choice of the submanifold Y, we can show that for all bad strata that contribute to the right-hand side of the equation, it satisfies the following conditions. The first bubble, the first component is rigid. By the first bubble, I mean the one that I define it to be the one that carries the first pairs of conjugate marked points. The first bubble is rigid, which means curves, the real curves of degree B1 that passes through those constraints carried by this bubble is finite. And also we can show that one and only one of the 3 special marked points is on the second bubble. So for example, in this picture, I have the first bubble carries both of z1 plus minus and x1, and the second bubble carries only z2 plus minus. So if we talk about the relative position of these 5 marked points, then we're actually talking about the relative position of those points on the first bubble. So the spirit of the Riemann-Fault compactification and the forgetful map is, since Z2 plus and Z2 minus run into each other at the equator, they bubble off. But as for the relative position of it with the other points, it's essentially just this node. Therefore, if we cut out this, therefore this cut out by Y condition is a codimension 1 condition on the relative position of these 2 pairs and 1 real marked points. So if we use these 3 points to stabilize the domain, then this codimension 1 condition fixes where this Z2 plus minus is on this equator. As follows. So cut out by Y specifies the position of Z2 plus minus with respect to Z1 plus minus X1, which means we fix the position of the node on the first bubble. Therefore, when we count nodal curves, reducible curves of such shape, we can count how many curves can serve as the first bubble first. That's a finite number. And once the first bubble is fixed in the manifold, these points are fixed points in the manifold. And this specifies where this equator is and where the node is. And then we count how many curves can serve as the second bubble, but it's also required to pass through an additional real point that's fixed in the manifold, which came from point on the first bubble. That gives you decomposition of this 2-component guy to the usual Welschinger invariants. In the case n equals to 3, the decomposition of the right-hand side is the same as above, but the decomposition of the left-hand side is a little bit different. Since we're in symplectic fourfold, those curves no longer intersect generically, but a dimension count gives us that only the following 2 cases can happen. The first one is the real bubble, the middle one is rigid, and the complex bubble is required to pass through it. So when we count such nodal curves, we count how many curves can serve as the real bubble first. And once this is fixed, we count how many complex curves serve as this bubble. But in addition to those constraints that are already on this bubble, we're required to pass through this prefixed curve as well. So this nodal count is a count of the real bubble times the count of the complex bubble with an additional real 2-dimensional complex curve constraint, which is the requirement that passes through this curve. This case is fun, it just decomposes like this. But the second case is when the complex bubble is rigid and we require the real bubble to pass through it. Now there's some technical issue is that, okay, let's suppose C1 up to Cn are those curves that can serve as the complex bubble, which are only finitely many. Then in the definition of Welschinger's invariants, to insert them as a constraint here, we need to not only know that the homology class of those curves in the second homology group of X, we also need to know their homology class in the complement of the fixed locus of the real structure. But we don't know that. So that is where this, as I mentioned in the theorem above, we need a finite symmetry condition in the dimension 3 case to do the decomposition. So the solution is we assume there is such a finite group, finite subgroup G of the automorphism group of this real simplex manifold, such that such a condition holds. This means that the fixed locus of G, fixed point. So this is the usual induced by the usual inclusion map. If G satisfies such a condition, then when we take the constants H1 up to HL, we take them to be G invariant. Therefore, those C1 up to Cn are just degree B prime J holomorphic curves passing through H1 up to HL. Like the formal sum of them also needs to be G invariant because they're determined by H1 up to HL. And therefore, their homology class is something that's G invariant in this group, which maps isomorphic to be here. We know each of the C1, each of the Ci is of degree B prime in this group, and therefore it's also determined in this group by this condition here. An example of this is when X is CP3, we can just take G to be Z2, the non-trivial element acts like a real hyperplane reflection here. So this case was first, this hyperplane reflection is first observed by Mikhalkin to show that some of the Welschinger invariants vanish. Basically, the idea is the same as here in his case. Final remark is that although we are using G in this proof, but we only need the existence of it. In the actual equations of those numbers, we can compute all of the numbers without this G. Okay, that's all I want to talk about. So I have told you about the splitting. I have told you about how to get those loading slowly. Told you about how to get this picture of the equations, which was here, but I just forget about that. Okay, so together with those picture of the equations before, the splitting gives me equations between Welshinger's invariants and also the usual Gromov-Witten invariants, so-called WDV equations. Yeah, here. Okay, I'll stop here. Thank you. Any questions?
Let's thank the speaker. Thanks for the talk.
Oh,
That was a really great talk.
thank you.
Right. Are there any questions?
Okay, one question. When you compact the R version of the Lee-Mumford space as Zi plus approaches Zi minus, does the Zi minus become an Xi in the compactifying boundary? No. So how it works is they bubble off just as usual. So say I have over here Z1 plus, Z1 minus, X1. I have Z2 plus, Z2 minus, and they both approaching here. What we get is simply a bubbling. Yes, the nodal point is on the real locus, right? Is it known how these invariants behave with respect to changing the involution phi in smooth families? That's going to be interesting to think about. I don't know any story about this, but the thing is, the involute phi is kind of, it's a somewhat rigid object. Like I don't know if you can really deform phi because it's an involution and it needs to be anti-symplectic. For example, P1 has only two on P1 there are only two real structures. So yeah, on P1 there are at least two of them up to conjugation, well, up to reparametrization of P1. And on Pn, I don't know if it's proved, or I only know two real structures on Pn as well. So, and in case like P1 cross P1, I think they have only, P1 cross P1 has only two real structures, I think, and P1 cubed has only three or only two, I don't remember, but in those elementary cases that I know, the real structures are like a rigid object. There are only a few of them, and they probably cannot be deformed in a family. Oh yeah, P1 cross P1 has three. Okay. Yeah, it'll be interesting if we have an example where these real structures can actually be deformed, or if we can like relax the requirement of this, if we can relax the definition so that it can be deformed. I was actually thinking about that as well, so it'll be interesting to think about. Okay, any other questions? Can you say again why you cut along the bad strata? Yes, that's the point of the proof, which is, let's see, yeah, here, because this actually, because this guy is not relatively orientable, and those bad strata are precisely those walls that obstruct this relative orientation. If they are not, if those things are not relatively orientable, we can't obtain such an equation, because when you can't even define intersection numbers. Like you can give orientation, you can give relative orientation with this map on this part, which it does have, but they're going to, this orientation is going to jump when you cross a wall, which is part of the bad strata. When the orientation jumps, the intersection number, of course, also changes. So to have this usual manifold intersection number thing working, we have to have relative orientation. That's why we cut it along the bad strata. So we have RMKLB bar. There are some bad walls in it. So we have relative orientation of evaluation map on both of this part and this part, but when you cross it, relative orientation changes. So this is bad strata. To have this nice equation of intersection numbers, so we cut this compacted space along here, and then cutting, we get like two pieces. Yeah. Now we get a manifold with boundary. they're going to be connected, of course. It's going to be connected, but it's going to be a manifold with boundary. But the good thing is now we do have relative orientation on this entire space, so that we can do this intersection. What can you compute using these relations? So we can compute all of the Welschinger invariants for P2, P3, real blow-ups P2, and P1 squared, P1 cubed. Later on in Solomon-Tukaczynski's WDBB for open Gromov-Witten invariants, they can also compute examples like Welschinger invariants for CP n for all n equals to 4n minus for all n that's modulo to 1, for all n that's congruent to 1 modulo 4. So basically you can compute a bunch of Welschinger invariants for some basic examples. Yeah, I don't know. On the other hand, this equations shows up in some physics literature as well. So there's a Alcolado. So his PhD thesis obtained the same equation from something that's related to physics. But yeah, I don't know about the details of that. Another question. Are the bad strata relatively orientable, or at least their double cover after cutting? I don't think so. Wait. Should be right, because they are. Since it's a boundary of already manifold, I suppose it should be relatively orientable, but they so on the top dimensional part of it. On the top dimensional part of it, it definitely should be relatively orientable. But when you cross some further codimension 1 boundary, like you have something here, cross wall, which are such kind of things. Back. This crossing, I'm not sure, maybe not, but just from the fact it's the boundary of the domain of the map that's already relatively oriented, it should be relatively oriented. The evaluation map restricted to the bad strata, I think. Yeah, I suppose it should be relatively oriented. Yeah.
Are there any further questions for the speaker? Okay, well, if not, let's thank Xujia again, and you're welcome to stay for the discussion section. Thanks very much.
Thank you.